As we get started. So first of all, I'm really honored to be asked to come back and speak again at this forum. I gave a talk in Seattle a little while ago about what Microsoft was doing to try and participate better in the HPC community. And one microphone. Okay. What we were doing to participate in the HPC community, and one of the things that I love most about working in HPC, and I've only been in this industry for 7 years now, is that it's really about how we make the world a better place, right? There's so much of the technology that gets built out of HPC that is improving things overall. Jim Gray wrote a great paper called The Fourth Paradigm, where he talked about these paradigms of science and how we went from empirical-based science to theoretical science and finally to computational science. The fourth paradigm for him was something called e-science, which was more of a data-driven type of science, which is a great topic, but not the topic of this presentation. But it's that computational side of things that's really important. And on the one side of the spectrum, we have exascale computing, which is driving this kind of gigantic computing infrastructure. And what I want to talk about today is the other side of that, this missing middle side of things. Like, how do we get more people doing HPC? How do we grow the HPC market? And one of the things I've been excited about doing is the Microsoft side of the HPC community. Is how do we do what Microsoft does? How do we stack them high, sell them cheap, commodity-based kind of stuff for HPC? And I've been really pushing our work at Microsoft to focus much more heavily on cloud-based computing, because I think that what cloud is going to do for us is lower the bar for people to do HPC. Just like Beowulf clusters were great because it was pretty easy for people to set them up. You could find all these people that could go and get 4 or 8 servers and wire them up with Ethernet, and you could do something pretty interesting in your office. Cloud computing is kind of like Beowulf 2.0. Somebody said that before me. That's not me, but it's I think it's true. So what I want to talk about today is what we've been doing on the data center side of things to make sure that cloud-based computing is actually going to be affordable and a reasonably smart thing for people to do. But first, let's remember kind of where we've come from. There's a lot of great history slides that came from some other folks. This is an old deck ad, which I thought was hilarious. If you're more than 10 feet away, you can't read all of this. But when hundreds of people in different places need the same information, or when people are waiting in line for their applications, one of my favorites is when your software costs are always higher than you planned on. Anybody like that? Yeah, anyway. What was so powerful about the attack of the killer micros, or the rise of Beowulf computing, was that it made things easier for people, right? Nobody went to these platforms because they were faster, right? People went to them because they were easier to get up and get running, and we kind of adapted our applications to be able to use those types of platforms because they were so much more accessible. And I think that's what's happening on the cloud side of things. Just to pitch what we do at Microsoft a little bit, we've been running some internet scale services for a long time. Some of them are pretty big. Like Messenger has 303 million users, and Hotmail there's 355 million users, and we run these pretty big services which require big data centers behind them. And we've learned quite a bit about how to build out those big data centers. We have a number of data centers located throughout the world. We're a little cagey about telling exactly how many they are. It's more than 10, less than 100 is the idea. And some of them are pretty big. We also have a bunch of content distribution networks which distribute data across the planet. One of the reasons it's important to have these gigantic content distribution networks is partially because you want to stream videos or games or do kind of cool Xbox type stuff, but it's also because on Tuesdays you get patches for the operating system. We have to get those out to everybody around the world. We are one of the most connected companies in the world. I think we're 4th largest right now, and the only one that's not a telephone company that's in that top 4 list. We have peering relationships with over 8,000 service providers worldwide. It's a huge, huge network. We also have these big data centers like Quincy, Washington. I don't know if anybody's ever been out to Quincy. That's right, there is nothing out there except cheap power. There's a big hydro dam located out in Quincy. We have a 27 megawatt data center there. Chicago, we just put up a 60 megawatt data center. Dublin, Ireland is about 50 megawatts, entirely run with air economized cooling system. In fact, there are no chillers there, right? We just run it off of the cold, wet climate that is Ireland. I don't know how many people have been there, So let's talk about what it means to build out these big internet scale data centers. Well, one of the things is a lot of times this is what we think about when we think about a data center, but there's all this other stuff that has to be built for if you're building out a gigantic multi-megawatt data center. For example, there are these gigantic diesel engines that are set up at the Quincy data center, which I was just at a few months ago. These gigantic diesel engines are set up. There are two of them. And as soon as we lose power, the first thing that happens is these rooms filled with lead-acid batteries kick in. And they can provide 22 minutes of power. The diesel engines actually take about 5 to 7 seconds to power up and connect themselves into the grid. If there are problems, we have 22 minutes. But they then power on, and the whole data center keeps running. There's all this stuff, though, that you have to build to run a gigantic data center, right? When you think about it. And it's part of what contributes to the cost of gigantic data centers. In fact, if you think about the costs, what really contributes to the cost of building out an internet scale data center, it's not land. And it's not even really the building itself. It's all of the mechanical and electrical infrastructure that goes into that gigantic building that you just put in place. Before you even put the servers in, right? You have to build this gigantic shell. And so what you really want to do is figure out how to reduce the mechanical and electrical costs associated with data centers. So Ed in his talk talked about PUE. Ed, I didn't see where I think he's back there in the back. But PUE is kind of this nice way, for those of you that don't know what PUE is, it's a nice way of talking about for every watt of electricity that goes into a server, how much energy are you spending on everything outside of that server, right? It's kind of the shorthand way of thinking about it. And different kinds of server architectures have different PUE ratings. And so when you begin to think about all of these costs associated with building out a data center, the biggest shift that you have to make is to think that the data center is the server. We spend a lot of time thinking about how do I build a good server, but at this kind of scale, it's how do I build a good data center, right? How do I build this gigantic facility effectively? How do I work closely with partners that are building out this server infrastructure to build these kinds of platforms that will provide this kind of scale? Now, the things that we learned as we went through this were, first of all, to start going through what we call right-sizing the server, which is eliminating components, figuring out how to work with our OEM partners to run these servers actually hotter. We run them quite a bit hotter than traditional data centers have been run in the past. We try to use air cooling wherever possible. I think Ed was demonstrating some of that stuff in his presentation. And we've eliminated chillers for a number of our server platforms. Anyway, let's talk about what some of these the power performance characteristics of our servers are. When you run, let's say you're running MSN or you're running any of these other big sites, you can kind of begin to really eke out this maximum performance per watt. We talk about green computing for HPC, but this is just internet scale stuff. If you can reduce the number of the amount of wattage per flop, you can do some really great stuff. So if you look at, these are old numbers, these are from a couple of years ago, but if you begin to look at the performance that you're getting out of a system versus how much you're paying in power to increase the wattage of that processor, you can begin to see that a 50-watt system provides some pretty good power, right? A pretty good amount of performance per watt per dollar. So a lot of the systems that we run inside of our data centers actually are running our lower power systems because they're providing better performance per watt. Now, certainly that's not true for HPC workloads, and we want to put higher performance systems in there. But this is an interesting thing to consider, because if we want to take our existing applications and scale those out to the cloud, we may have to start thinking about how do we write applications that run well on these lower power processors. So let's talk about what we've learned at Microsoft. In 1989, we started building out our first data centers, and we built them like everybody else, where you build this gigantic room, you put a whole bunch of servers and a bunch of racks, and your PUE rating is about 2 for that kind of system. It's not great, right? You're chilling this entire room. Our next generation data centers were 1.4 to 1.6 PUE because we started using rack-based systems like the rest of the industry did at that point. I have a friend that used to work at Sun, and when they did network.com, they had racks, but he said, we built everything exactly wrong. We went and built our data centers in Manhattan. It was the most expensive real estate and the most expensive power that you could possibly get. So as we start moving out, we start thinking, oh, okay, so how do we build the data centers where things are much cheaper? And how do we start doing things like containers or pods as a way to be able to reduce the PUE rating? And you can get down to about 1.2 to 1.5 PUE. The current generation of systems that we're building, we call them IT pack. They're very similar to some of these other containment systems. Are basically a data center in a box. Right? All of that stuff that was sitting outside those servers in that earlier slide, it's all in a single box. The batteries are in this box. The chillers are in this box. The airflow system is in this box. In fact, it's 4 boxes. You kind of slap them all together, and it turns into a little data center. It even has a abiatic cooling system, water-based cooling system inside of it. But this system, you can really drop the PUE on. In fact, if you don't have those big diesel generators on the back, you can get down to 1.05 PUE. Right? In fact, this is the infrastructure that Bing uses for all of its search across the planet. The great thing about Bing also is that it's a fully distributed application. So if you lose Quincy, Washington, it's OK. We redirect to one of our other data centers. Wouldn't it be interesting if we could write HPC applications that work that way? I think that's an interesting challenge for us as an industry. Let's talk about the Chicago data center, just as an interesting example. This is something that we are never going to do again. So it's kind of like the last of the big data centers. This is a $500 million investment for the building. Right? It's 700,000 square feet, 60 megawatts of power, 3,400 tons of steel. I mean, it's just like these are these gigantic endeavors, right, to build out these data centers. And the thing is that it's a lot of money to build out that data center, right? Typically, it's $10 to $20 million per megawatt of power for a data center. They're cool, right? It's this big chest-thumping kind of exercise. But really, fiscally, it doesn't make any sense, especially when you can go to these IT pack configurations, which enable you to scale a little bit differently, which I'll get to when we move on. When we look at these types of clusters instead, we work very closely with our OEM partners, and we can just add units as we need them. They don't need a lot of infrastructure either. If you go out to Quincy, Washington, and anybody who's coming out to supercomputing and wants to take a 3-hour drive out to Quincy, Washington for a data center tour, I'd love to take you. If you go out there, the original IT packs that we had set up, they were just sitting out in the sun on a slab of concrete. And customers would come by and they'd look at it and go, well, that's not real. That's a toy. You can't leave these things in the sun. And Quincy is in eastern Washington. It's 100 degrees during the summertime there, and it snows in the winter. But actually, with those kinds of systems, you can. We actually put a roof over that building so people would take us more seriously. There are no walls, though. They're just screens on the side of the building. But you just, it's a big slab of concrete. You just add more of these modular servers as you need them. It's a big container filled with hundreds of servers. So this process has been working out really well for us, and it enables us to dynamically scale out our data centers. In fact, you can begin to see things like this type of configuration where you just keep adding in more and more of these modules over time, and your data center keeps scaling as you need it. It's kind of like a just-in-time data center, right? When you're building that, kind of Chicago-sized data center, that's years and years of planning effort, right? But when you're building something like this, you set yourself up somewhere where there's good power, and then you can scale out as your needs increase. So it's been a pretty interesting exercise. So as we built out these better data centers, it's really been about how we really think about data center design integrated with server design. And that process has worked very well for us in terms of building internet scale systems. But I think it's also the key for the Beowulf 2.0 side of things, right? These gigantic commodity systems, because they run all kinds of workloads. They can run, mail servers. They can run search algorithms. They can run, Messenger, Xbox, all of that kind of stuff. If we as an HPC community figure out how to use those low-cost computing resources, this market can really grow, right? These aren't the super expensive, high-price HPC SKUs. These are commodity systems, right? In the same way that Beowulf clusters were commodity-based systems. So it requires a little bit of a shift for us. I don't think it's as radical of a shift as going from traditional kind of supercomputing infrastructure to Beowulf clusters. But I think it is a pretty powerful shift, and it will continue to reduce that barrier for computing and make it possible for more and more people to do HPC. I think it's going to at least double the size of the HPC market, just as the HPC market doubled around 2004 to 2006 as Beowulf clusters came in to play. So that's the end of my presentation. If you want to understand more about our data centers and kind of what we're doing, we have a blog, of course, and our Global Foundation Services team has their own website. So thank you.